Today we will conclude the analysis of service robots, in particular by looking at very anthropomorphic robots, either constituted by upper limbs, like these two cases, or a full-body humanoid. And we will conclude with some comments on the mobility and dexterity of these structures. The second part of the lecture will be devoted to starting analyzing components of any of those robots that we have seen in these few lectures. And we will start in particular to considering actuators and transmission elements. So, what are these two guys? On the left, the Justin robot. The name came out from the fact that it was completed just in time for a presentation at the fair, at the Automatica fair. You may recognize that the two arms are two lightweight robots that we have already seen, so 7 degrees of freedom each, plus additional degrees of freedom in the torso, including the head. The head has also two cameras. The end effector are equipped with force torque sensor. This is just a pictorial view. You will see now the actual devices. And completed by two hands, still developed by the German Aerospace Center, to make it a fully performing upper body. There is no mobility. In fact, this robot has been placed on a wheeled mobile base with 4 revolute and turning wheels, but this is not of interest to us. On the right-hand side, you see another prototype by still German, by a national project on humanoids. Again, you can recognize the head, the eyes. They have independent mobility so that you can gaze at object while turning your head or keeping the head fixed and looking at the object that you want to track. And the structure is more or less similar. There are a multitude of such devices now around the world. So let's consider Justin. And we have here now a very long video, I should say. Unfortunately, you don't get the audio, so I will try to comment it with you. Selected parts. Again, I invite you to go to the website and download the zipped folder where you can find the whole video in full quality. So this describes the system. Start from the kinematics, the components, and then moves to the software architecture, which is very important for devices like this. Have so many degrees of freedom that has to be coordinated, but still you can recognize some modular structure: the right hand, the right arm and the hand, the left arm and the hand, the torso, the visual system, the grasping system, and so on and so on. You have to have local controller which provides mobility, but everything should be coordinated and driven by the actual task. So in this video, you will see more or less all components, including the way in which the system is programmed on remote computers, and then those programs are downloaded in executable real-time code. And this is very flexible, thanks to the control architecture. And then the last part of the video will present some exemplification of the task that this robot can make in bimanual manipulation, so using both hands. Okay, so let's start the video. no audio. So here you see that there is stereo cameras, laser scanner as sensing devices, 2 lightweight arm with 7 degrees of freedom, a torso with 4 joints and 3 motors. Then each hand has 12 actuated joints, so multi-fingered hands. The overall weight is 45 kilograms. There are a total of 43 elementary degrees of freedom, so joints, all of the Revolut type in this case. And the kinematic design was such that you can take things on the ground and bring it up to a 2-meter high location. So this is the composition, and maybe I can stop the video here, in individual parts. In individual parts where you can recognize as devices, so the hand, left or right, the arm, left or right, the single torso. And these devices are controlled in motion at frequency which varies from 0.3 milliseconds to 1 millisecond. Okay? And you have here a torso controller, an arm controller, a force controller for the hands, because the hands are supposed to handle things. And then you can combine this into position control, then you interpolate trajectory, you solve invert kinematics every 60 milliseconds. While doing this, you can also impose some Cartesian impedance. We have seen some example in the KUKA lightweight demos where you can use this compliance, so being more stiff or more compliant in different direction. And impedance is a generalization of this concept where you can change the apparent inertia of the system at the Cartesian level. You may have routine which prevents collision avoidance in real time. They run at 3 milliseconds. And all these components and software pieces are coordinated at the discrete level of events by a state machine. Okay, so the state machine monitors in which condition you are and which part you should activate and run, which can be run in background, which have higher priority and things like that. On top, you can see other things. For instance, there's the camera, which is a stereo camera here. So vision, you process images, and you have a word model from the images. So you recognize object, and when you move this object around, you have to update your word model, both logically, because you're taking one part and moving it to another place, and then also verify that the image that you get is consistent with this change of the word state. You have also input device and a graphic user interface, because the human has to give high-level commands. You have a path planner, which generates some motion, which avoids obstacles based on the word model, but still you need to do collision avoidance because things may change while with respect to what you have seen before and with respect to the motion that you have planned. So a collision-free motion planned in advance may then hit in reality things, so you have to control the situation and update your commands, motion commands. Well, I think that this is enough. So all these parts are located to a distributed computing system. So different machine or different units, computing power units, which work in real time. So they typically work, most of these work under real-time operative systems. And let's continue now with this video. Yes, it goes around. And now you will see that these blocks are connected in big blocks. This is the real-time part. And here you have VxWorks or QNX as operative system. You have a block in Linux and so on. And this is a way of programming. You program it through MATLAB or Simulink interfaces. You generate real-time code automatically, and you download to the target machines, which execute things. It's a very convenient way. So for instance, here you have given sinusoidal commands to the joints, and you have this motion, sinusoidal commands in current, for instance. And now, what is the capability of this system? This is gravity compensation. So the own weight is sustained so that you can move it around without, like a floating object in space. You can couple the two-end effector with some stiffness. If it's very stiff, they move all together. So you move one hand and the other follows. If it's compliant, there will be some oscillation. This video was made at the time of the German soccer championship, I mean the World Championship in Germany. So they are using these soccer balls for showing how you can press and be very accurate in exerting forces and controlling position that you don't lose 3 rolling balls hold together. These are more conventional tasks where you can impose some force by modeling what are the, like a virtual spring placed between the object and the two hands, so that you can exert in a compliant way forces that helps you to grasp firmly the object. This is another way of doing things, which is fully defined at the level of the object itself. So in the Cartesian space, but the focus of the controller is on the mobility of this object. And around the desired trajectory and the desired forces, you build all the controller. So you can, for instance, perturb the structure, but he's commanded to keep the box in place, so he's not moving the place, but accommodating the external forces like we would do, I mean, a bartender would do if it's holding its tablet and then accommodating a collision avoidance while keeping the object in part. There are other systems. This is the collision detection that I showed you already in another video. And finally, task-oriented programming. You can simulate the system in advance with a graphic interface. You can plan trajectory. For instance, you can go around this bottle in order to take this glass. Once you have a plan, you download the motion in the Cartesian space, which through the inverse kinematic is transformed in motion of all the joints of the structure, maybe with some hierarchy of allocation of motion. And finally, you can complete tasks in this way. For instance, this is quite a challenging task, and you use the bimanual manipulation in this sense, because you would not be able to do this with only one hand, so you're holding the part and you're doing exactly what you would do at the human-like level. You can imagine that programming this task, if I have to think about the motion of all the joints, would be impossible. So the idea is focusing on the Cartesian level, and in particular on the specific task, and trying to, once you have planned the elementary motion at the end effector level, you try to bring the resulting information on which motion you should execute in order to realize that task at the level of the joints. Remember that at the level of joints, there are the motors. So eventually, you have to command the motors to move the joints. But the actual results and the performance is evaluated at the Cartesian level. Okay? Again, these passages between spaces, Cartesian space or end effector space, and joint space or actuation space, where you move things. Okay. Let's move on. So these were only upper bodies. Of course, you would like to see the full pictures, like in the famous movie by Fritz Lang, a humanoid. And there has been, over the last, I would say, 25 years, a lot of great advances in humanoid robots. This is a small-size humanoid dated 2003, and its name is Spino, so it's like an Italian name, but the company, ZMP, is an acronym that stands also for zero moment point, which is a technical concept used to locomote, to keep locomotion, so walking without falling, so in dynamic condition. So it's nice that they have used a technical word for qualifying a company. But probably the most famous humanoid that struck the general public was this project by Honda, who released the first Asimo. Actually, Asimo is not sold at all. It's just a project by Honda, owned by Honda, and distributed at very few research labs in the world. So this project started back in '86, so quite a long time ago, and evolved over the years. They made first a huge, relatively huge robot, 1.80 m or so, and then they decided for a second release which was smaller and more comfortable for a human that should interact with it. The name comes from Asimov, of course, so it reminds a science fiction writer. There are a lot of degrees of freedom distributed, not only in the left and right hand, but also in the legs that allow the most natural locomotion possible. You will see in the videos that the locomotion of Asimov, at least in these videos, was not really natural. In particular, these humanoids tend to walk with knees which are bent, so to have a larger stability. Under the feet, there are force sensors measuring the pressure and alerting if, while walking, the robot is losing the equilibrium, so that you can compensate. And for compensating, remember, you can use also the remaining degrees of freedom. You don't have just to move your legs. You can balance yourself by using the upper limbs. And this is a very specific feature of humanoid and of humans, of course. So let's see. For instance, in this exposition in 2003, so we're talking about more than 15 years after the first presentation of Asimov, this version of Asimov could climb the stairs. And here you can see the second series, which is the smaller size, coming into on stage, I would say. And this is the type of locomotion. You can see that there is a coordination also of the right and left hand, and this is essentially for guaranteeing a better dynamic balance of the whole locomotion. In this video, you don't hear Asimov talking, but Asimov talks and listens to you and can understand some vocabulary. So there is all the part which relates to the cognitive interaction between the human and the robot itself. But here we are focusing more on the physical mobility. And you can see in these simple steps that the robot has degrees of freedom placed everywhere, at the knees, at the ankle and also close to the feet. In particular, the two feet can rotate on this side, and this allows also to recover some perturbation on the sides in a very efficient way. Of course, the motor that can move the upper parts are much stronger than those that can move the lower part. But in fact, all the weight goes down to the feet. So it's a very critical issue to size this motor capability, torque capability of the various motor in order to limit the total weight and still have enough power where it is needed in order to walk and keep balance. Asimov, with his vision system in the head, could recognize its environment and walk, avoiding collisions or avoiding object on the ground, and to be to provide you a complete picture, one should say that later on, in the last few years, there are much more dynamic motion in the latest version of the same, essentially the same hardware, but what was improved was the software part. So the capability of planning motion in a natural way and controlling and executing it in a very, let's say, again, natural and continuous way. Here, a short, very short video shows also the capability of looking at the human and then walking backwards while balancing and mimicking. So this shows also that, in fact, it was really real-time command of motion, not a pre-planned path for this humanoid. And over these decades, there has been many humanoids built around the world, mainly for research purposes. Sony was an exception because this SDRI 3X and the later Curio were actually being sold. This is a humanoid robot built in China. China, as we have seen, is an emerging country also at the research level in robotics. And on the left, you see the first of a series of Japanese humanoid. HRP stands for Humanoid Robotics Project, launched by the academic community together with some manufacturer like Kawada Industry, which is a huge electromechanical company in Japan, which built actually the robot, but according to the instruction of researchers of several Japanese university. So now this is HRP2. You see 150 centimeter, 30 degrees of freedom distributed on the body, about 60 kilogram of weight. So human size, dimension, and weights. Now they have reached HRP4 as a model. And this has been a huge success in terms of scientific achievement. Talking about Sony, I told you already that the Sony Aibo, the small dogs, four-legged dogs, went out of the market in 2006 together with this small humanoid, Sony Curio, which was at that time one of the most sophisticated one. It could balance himself on a surfing board or grasp object launched in their vicinity, so changing in real time the attitude of the body in order to stretch a hand and grasp the ball, which was recognized by the vision system, and its trajectory was predicted by the onboard computer so that you can do this meeting in the right way, and dancing in coordinated way. This is I will show you only a small part of this video. Actually, if you listen very carefully, this is Japanese pop music, okay? So, but anyway, the idea is to have them move and show the accuracy of motion. They were controlled separately, so listening to the music and taking the rhythm of the music so that they appears to be quite good coordinated between the single robots. Okay, you can find more of this on the web as usual. Now let's talk about the latest famous humanoid robot, which is produced in Europe by a French company which is called Aldebaran Robotics. His name is, or her name is Now. Now it's used in the RoboCup league, I mean the legged league, the one that is intended to compete with humans by the year 2050. The description, the Now is relatively small, 57 centimeter, but quite light. It's made of plastic, actually. So this is why the weight is so low. But you can describe, and you can see on the right-hand side, the kinematics of this robot exactly in the way that we will describe the kinematic of fixed base manipulators. This is why I'm showing this picture here. You can see starting from the bottom, you have 1 degree of freedom of the revolute joints, which means that the feet can rotate around the sagittal axis. Then you have another degrees of freedom of the revolute type like this, and if I can balance myself, this means that you can stretch your feet up and down. And then you have 1 revolute joint at the knees, so you can bend the knee like this, okay, and stretch. And then you move up, and here you can see a combination of 3 joints at the ankle, so that you can bring your leg in front and back, but then also rotate it on the side, and have an additional rotation which opens in this way your leg. And the same occurs on the other leg here. Then you have basically a fixed torso, 2 degrees of freedom for rotating and elevating the head, and then the degrees of freedom of the single arm. So you can imagine that the whole body is fixed and just 1 arm is moving. Then this is exactly the kinematics of a manipulator arm with fixed base, but the base is at the torso of this robot. The same for the other. And as long as the robot walks and keeps 1 leg in place on the ground, then all the rest has a 3-branched structure of serial parts, from the sustaining leg till the right-hand effector, to the left-hand effector, and to the other feet. Okay? So you can describe exactly in the same way also the kinematic, the configuration of the robot and its mobility. When you give velocity to the single joints, you can compute what happens to all the parts of the body, and then you predict if you're going to be falling or walking in the right way. Of course, it's much more complicated, but the scheme is the same. And here we have a commercial video that shows the capability of now. By the way, we have several now in our department because we have a RoboCup team, SPQR, plus in our lab we have 2 additional now that we use for studying visual servoing and human-robot interaction with humanoids, physical interaction. And here you can see now keeping balance, not falling. So adjusting its internal configuration by feeling the situation. It has force sensing on the feet. It has accelerometer to measure the direction of gravity. It can talk, it can hear. It has soft hands. I mean, they are not capable of sustaining heavy load, but enough for shaking hands with you. Here are playing during the soccer team, the RoboCup soccer team. And here you see how now can stand up by himself with a very sophisticated sequence of motion. First, recognizing in which direction he's laying on the ground. And for doing this, he needs the accelerometers. And this is Bruno Massonnier, the owner of this company. And of course, being a commercial, you can see him doing very sophisticated things. Okay, so this is now, and some of you, if you continue in the robotic stream, even artificial intelligence stream, you will be working for your final thesis probably in the master on such devices. So we have seen mobility with many degrees of freedom, humanoid walking, but don't forget that the dynamic stability and balance is a long-standing topic, and you have already seen in this historic video issued in year 2000 some of the early attempts to keep balance while moving and not just in static condition. And this is a requisite strictly necessary when you have only one leg, like this object here, so that standing in equilibrium on this single leg with very few degrees of freedom, it's a very hard task, because it's enough that somebody opens a door and this lateral disturbance will let you fall, unless you start jumping. Start jumping and sustaining your equilibrium in a dynamic fashion and adjusting the place where you put your single feet so that you can keep equilibrium. This picture, this is not a video, it's a picture with a stroboscopic LED, you see. This is the evolution, actually starting from here, the evolution of the feet touching the ground and then jumping more to overcome this obstacle. Okay, so taking a position at the instant where the feet leaves the ground such that the landing part will be far away from the obstacle. And then going back, because this would tend the robot to fall, so recovering equilibrium by compensating and jumping back and forth. While doing this, the upper body had another leg, was moving like in a sinusoid because it was jumping and going like this, progressing in one direction, while the leg was winging to the front part, then reorienting and then jumping again and landing and so on and so on. And you can see this. This is a variant of the same one-leg hopper. So this is keeping balance. It could stay on place, or by slightly inclining the upper part, direct in one direction. Okay, so move in one direction, then sustaining, stopping, and then going in another direction, and so on and so on. A very difficult things that requires something that we won't see in Robotics 1 course, because it requires the consideration of the full dynamics of the robot. So it's not enough to say what is the velocity of the single, let's say, single extensible joint, which is the leg, or of this orientation. This is not enough to realize such dynamic stability condition. You should take into account masses, inertia, and other phenomena. But anyway, we can conclude by these two additional video. This is the same in the similar spirit of before, but this is a two-legged robot doing a somersault. You have seen this already. This is a slow motion, and then rotating and falling, and then recovering equilibrium. You see that how the dynamics is relevant here. And finally, this is another system. Actually, I like this video because this is made exactly with the same robot, with one of the two robots that we have in the lab, the KUKA KR5, equipped with a camera, with an end effector and a ping pong racket, okay, and moving in such a way that balance this ball forever, I would say, forever, okay? Unless there is a big disturbance that would move around. Let's move it. Let's see it again. There's a big perturbation that would move the ball very far away. Between one cycle and the other, you can recover and adjust position and orientation of the racket such that this continuous bouncing or juggling continues long enough. Okay, I think that you're probably saturated by seeing so many videos and you're lost in what is our program. I think that I hope I have given you enough motivation in order to understand that we need to go inside this structure and understand the basics of the components, sensing and actuation, and mechanical structure of the arms, and then the basic of describing geometry and mobility, so kinematic, differential kinematic, and planning motion. Before doing this, I have a couple of slides which comes together with those on industrial robotics, which mention the state of diffusion of service robotics. And these are data from the latest World Robotics report in 2014. And here you see service robots in 2013, the red one, and 12, so the year before, in different fields for professional use. You see medical, they stay quite at the same level. This is the number of sales. More have been sold for logistics, and this may include the mobile robots that are used, for instance, in the Kiva system for the logistic of Amazon deposits, using the field, so open field defense, again, a small reduction. And this is the forecast for professional use, but we are talking of this number, or maybe the most significant number is the one on top. So in 2013, there has been 21,000 service robots sold. Remember that the number for industrial robots was 180,000. So this is the relative size of the markets. But still, it's a growing market. So this is why I brought these things here. And again, this is two areas of entertainment and household, so not for professional use, but for personal use. And the forecast says that there will be an increase, a large increase in the period 2014 to 2017, especially in the household part. So these are predictions, of course, but based on market analysis, so this is important. One thing that I would invite you to do is to browse through several of these websites. For instance, you have seen one collective videos of year 2000. You can find more than 440 research clips in this website by the Robotics and Automation Society of IEEE. Unfortunately, you need to log in with your user ID and password, which means that you have to become a member. But I strongly encourage you to become a member of this society or of other society of IEEE, but we are talking about robotics and automation, so this is our concern now. Because it's very cheap, you get access to a whole bunch of possibility of information, technical and scientific. And it's a good path for building your own professional career later on, either if you stay in academic or if you go to industry. It's the largest professional society in the world. There are other websites that you can access freely. For instance, the service robotic website of the technical committee of the same society, where you can find information about service robotics. Or you can browse the European Robotics Research Network. This site has been switched off, I mean, no longer updated since 2012, and this is the new site. But in the old site, you find a lot of information about former European research project and galleries of robots, of other educational material that you may use. And finally, again, this is our YouTube channel with our personal latest research results. So you can find them there. Okay, you have any question on this part so that we can switch and move to some more technical aspect? Okay. Everybody is receiving my emails? Okay. Fine. So, I wait for a start. It's okay. So, robot components. So, let's do some anatomy. Let's start with the most inner part, which are actuators. Before doing so, we take an overview, a system view of robots, and essentially we convert commands, so a planned sequence of elementary actions, into changes of the word, so performing action in the working environment. Performing action means whatever you need, even moving one object from one place to another is changing the state of the word, or assembling things, or performing some mechanical operation in an industry environment, or sustaining a patient for moving out of its bed, and things like that. For doing this, the robot uses several units, so the mechanical parts, the sensing part, actuation part, and some generically, collectively defined supervision, which may include planning and control capabilities. And if we look at these units in a bit more detail, what are the mechanical parts? Now we are focusing only on robot arms, so fixed base robot arms. So we forget about locomotion, wheeled bases or legs and things like that. Just the elementary robot manipulator. So for us, this will be a connection of rigid links. So we assume that each link is rigid. It's not deforming under its own weight or under the effect of forces. This, of course, is an abstraction, but it's very concrete in most of the time. And these rigid links are connected through joints, elementary joints, because there are several types of joints. By this, I mean that they give only 1 degree of freedom, which is either of the rotational type or of the prismatic type. And we use sometimes this way of representing joints. So this is a revolute joints, and this is the joint axis. And there's an angle theta and a velocity theta dot, saying that we are rotating around this joint, which means that if these joints connect some body with another body, before and after the joint, this means that this body will rotate thanks to the motion of this joint with respect to this body. Okay? There will be only one elementary motion, which is a rotation around the joint axis by a quantity which is specified by this speed. Okay? Of course, this body can be after another joint, and when I'm moving this joint, I will move this body and all what is beyond, especially if I have a serial kinematic chain. So this is the notation for a revolute joint, while we may use this kind of rotation of notation for a prismatic joint. And in this case, this sketches exactly the same situation. You have somebody here and somebody there. And when I'm moving by, let's say, a distance d and some velocity, some linear velocity dot, along the same joint axis, so I have a joint axis which is exactly the same as before, but I'm not rotating around it, I'm translating along this. And what happens is that this body will be more distant than before or closer to the previous one. This is the degree of mobility that a prismatic joint gives to the following links. Okay? So this is the basic concept that we will use. Of course, within the robot itself, within even a single arm, we have seen this decomposition for a full humanoid. But the same holds true at the lower level along the single arm. So we can characterize the main joint axis, the first one, which are typically used for moving the end effector around. So this is the supporting structure. Typically, you have three joints, at least three joints doing this task, so moving the end effector around in position. Okay? And they can be any combination of prismatic or revolute joints. Then we typically have, not necessarily, we have revolute joints which constitute the wrists, and this wrist may be spherical or not, depending on how these joint axes intersect. And this gives what is called dexterity, so the capability of first structural joint or supporting structure will move my hand around, and then with the wrist I can reorient and change attitude and pose, and this is the dexterity achieved by this part. Then I have the end effector by itself, in our case my hand with its finger, so we may have additional internal degrees of freedom. Most of the time we have only a simple gripper for an industrial robot, and we don't include the fact that the gripper opens or closes as an additional degree of freedom. Okay, this is related to the task, not to the mobility. Okay, so these are the basic subpart of the mechanical units of a robot arm. Then for the sensor units, we have already mentioned that we will make and we will study the large variety of possible sensors by classifying them in proprioceptive or exteroceptive. So proprioceptive are sensors that provide information on the internal robot state. So which configuration the robot is having or the arm is having, if folded or stretched, or which single value of the joint variables, those variables theta and d, for instance, are currently assumed, and in addition also the velocity of these joints. These are the typical proprioceptive sensors. There are other sensors that can be used as proprioceptive. For instance, we may have at the joint some joint torque sensor which measure the torque transmitted between the motor moving the link and the actual link. We will see that this is the case when, especially when we have an elastic transmission, and then we may need to measure this transmitted torque. This is again an internal information. And then there's a whole bunch of exteroceptive sensor that provides to the robot information about the external world. And they may involve contact, like tactile sensing, like skins for the robot or skins for the finger of a dexterous robotic hand, or just vicinity. So proximity sensor of the ultrasonic type, infrared type, laser type, up to vision that provides information without contact. Another typical exteroceptive sensor is a force torque sensor. We have seen it mounted as an end effector component of an industrial robot in one of the slides a couple of times ago. And this measures the exchanged contact forces with the environment. Typically, these contact forces arise at the tool tip, but are measured in this device, which is mounted on the wrist of the robot. So it requires some kinematic transformation in order to extract the original forces and moments that are measured by this device. All this goes into the large class of exteroceptive sensors. Again, perception on one side, action on the other side. We have actuators, actuation units in general. So we will see a few of them, and this will be our next topic. So motors of different nature, mostly electrical motors, in some situation hydraulic, especially if the robot needs to carry heavy loads, or pneumatic for special purposes, like for opening and closing grippers. And among the actuation units, we can also consider not a hardware part, but more a software part, which are the motion control algorithms, how these motors are used and commanded. And this is why we make a slight distinction. Pay attention. Motors are the brute components. If we close some feedback loop around this motor in order to achieve some desired performance, then we have a servo drive, which is a controlled motor. So a motor which delivers torque or velocity according to desired profile in times. Okay, so in our case, we are interested in servo motors, and this is why I put under the actuation units both the physical motors and the control algorithms. And finally, this is very broad, supervision units. It's the brain of the robot. So whatever is involved in planning tasks, planning trajectories and their actual execution, and reasoning about dynamically changing words and information that comes from perception. This is a part of artificial intelligence which is called cognitive intelligence, because it's reasons not on a static situation, but on continuous inputs coming from the sensors. It's not like playing chess, where the number of moves is very large, too large, actually, to be managed by a normal human, but is prescribed. The rules are prescribed. From one state, you can only have a finite number of options for the opponent, and so you have to reason on this and predict what will be the final goal according to the desire of winning the game. In robotics, this is not the case, because sensing are corrupted with noise. There is a probability of things that happens or not. There are different events that they may enter into the picture. So the reasoning which is behind the optimal choice of an action is much more involved and requires some developed tools from artificial intelligence, those that you will study in the courses of machine learning and artificial intelligence. Okay, having said this, just as a matter of introduction, let's go into the actuation systems. The first thing that you should consider is that, again, for the actuation, you may have several components, and it's convenient to focus on the flow of powers around these components. Okay? Here, we have a servo motor. So this is maybe an electrical motor, any type. You can buy small electrical motors like this for 20 euros, okay, for home entertainment or things like that. But this is not just the motor, it's a servo motor. So it's a controlled motor of the electrical or pneumatic or hydraulic type. Okay. Now, this servo motor receives some power and produces some mechanical power in output. And this mechanical power, through a series of transmission, mechanical gears, becomes some useful final power for moving the links of the robot. Okay? Now, this actuation is typically a high level of power, but it's commanded through a low-level power signal. This is the control signal, which is amplified by some power amplifier. Those power amplifiers are physically located within the cabinet of the industrial robot, except for some very advanced recent research robots where the power components are inside the robot itself. So they were able to miniaturize and provide enough thermic dissipation to mount those elements on the body of the robot itself. In this amplification, you need some power supply. Those robots work with battery or with 220 or 380 volts electricity. So here you can make a balance of power entering and exiting this single component. Now, while you're doing this, somebody may get lost. So you have some dissipation. For instance, in the transmission, you may have friction. And every time you have friction, you lose something. This is why you like to lubricate very accurately your mechanical transmission elements. Or at the level of an electrical servo motor, you may have electrical dissipation, like eddy currents lost in your circuits. So you don't have full isolation. And then you have extra sparkle, which may be also dangerous if you're using an electrical motor in a very critical environment, for instance, where there are chemical materials, things that could explode and something like that. So you have dissipation everywhere, and you should take into account this. Of course, there are a couple of concepts from physics that I have added here. Let's start with the last one. Each component has some efficiency, which is the ratio of the power going out with respect to the power going in. If there were no dissipation, the efficiency would be 100%. Okay, so nothing is destroyed, nothing is created. Okay, of course, this is only the ideal case. The other important thing is remember what is power. This is physics. In our case, power can have several natures, so electrical, hydraulic, pneumatical, mechanical, and so on. Talking about mechanical power, so it's the product of a force times the speed realized by this force. How do you measure force? In which units? Newton. How do you measure speed, linear speed? Meter per second. So, let me make this very complex passage here. The first one is Newton times meter per second. Okay? Well, this is if you're applying a linear force on an object which has some velocity, like in the prismatic joints that I have canceled here. Okay? What about a revolute case? Well, same thing. Product of torque times angular speed. Here we have an angular speed and some torque which will rotate the distal body with respect to the proximal body. Okay? How do you measure torque? Newton? No. Remember what is a torque. Torque is also equivalent to a momentum. So you have a force here, and if you compute the effect around the point of distance d, this force times this distance gives a momentum around this point. Okay? So, since a torque can be seen as the product of a force times the distance, what is the unit of torque? Newton meter. Okay? So we have Newton meter. And I write it on purpose like this. And what is the unit of angular speed? Radian per second. Okay? Now, since radians is adimensional, you can see that this writing or this writing both give Newton meter over second. Okay, which is the unit of measure of power. No matter if of this kind, this is mechanical examples, but the same could be applied to any other power. This is why it's useful to work into reason in power terms, because the fact that the physical nature of this power changes doesn't matter. You can always express it in Newton meter per second, or in another equivalent way, for instance in watt, or for instance in joule over seconds. Okay, so don't forget this analysis, dimensional analysis of physics, because sometimes you write an equation and there's a mistake, and you don't realize that there is a mistake, but you would if you look at the dimension of the single component. So you understand at some point there is some term missing because I have apples there and oranges there. Okay? This is a very useful tool. Okay, so this is our chain, and we have some power dissipation. Of course, we would like to minimize dissipation and have the highest efficiency. So let's start from the bottom. Let's start from transmission element. So suppose that we have some motor producing torque. Imagine that it's an electrical motor, so we are applying voltage, a DC motor. We will see this in detail next time probably, because now it's getting a bit late. But you're applying voltage, so the motor starts rotating and applies some torque to a load that it's appended at the end of its axis. Okay? Now, typically, we don't have such a direct drive connection. So the load is not mounted directly on the axis of the motor. And there are several reasons for doing this. And all these components are mechanical gears which constitute a transmission. So what is the role of transmission in general? Here I have listed some. There may be more, but these are enough sufficiently important by themselves. So first of all, the first one is more, it's not very detailed, it's more a principle. We want to optimize the transfer of mechanical torque from the actuating motors to the driven links. Remember, we have to move the links. We don't move the joints. We move the links. And for moving the links, we need to rotate or translate the joints. Okay? The joints have no mass. The links have mass or inertia. So it's important that we move around the links. Even if we parameterize, for instance, their motion with, let's say, the speed of one joint. But what is moving actually are links. So the links should be moved in an efficient way with our motors. The second item is the very critical one. Is also the reason why these transmission elements are also called reduction elements. Reduction element. Why is that? Because if you have an object which is able to scale down the speed, for instance, the angular speed of rotation of a motor, which is very high, typically 300 rounds per minute or something like that, then you put a reduction or a transmission element which reduces this velocity. And the output velocity is 1 radian per second, 2 radian per second. Okay. Why are you doing this? You have so much speed and you want to reduce it. It seems crazy. Okay. But in order, if we assume that there is no dissipation in the system, you have a conservation of power. Okay? And the power, this conservation implies that if you had low torque on the output of the motor but high velocity, after the reduction of the velocity, you will have low velocity but high torque. And with high torque, you can accelerate larger masses with the same motor. So the reduction element is fundamental in order to bring up the torque capability of a motor. So you can buy a motor which has rated output on its axis 1 Newton meter, but if you have a reduction element of 100, which means that the load will rotate 100 times lower than the motor, you have also an amplification by 100 of the torque. So you have actually available for accelerating your link, which mass whatever, 100 Newton meter rather than just 1 Newton meter. Okay? So don't be disguised by the fact that if you look at the data sheet of the motors, you may have very small output torque. Why is that? Because what is missing is the reduction element. And you can mount different reduction elements for the same motor in order to obtain the best performance. So this quantitative transformation is fundamental. We will make some computation later on. Then there's a qualitative transformation by the motion transmission element. So typically, electrical motor is almost 99% of the time, and I would say 100% of the time in robotics, is a rotating machine. There are linear motors, but they are not used in robotics. Okay? So this is rotating, and x-axis is rotating. How can I transform this rotation into a translation of a prismatic axis? I need a transmission element, which converts qualitatively a revolute rotary motion into a linear motion. Okay? Or, what if the motor is mounted in this direction and I have to rotate the link in this other direction? I have to change direction. So I need some G-rings that realize this change of direction. If you're a motorcycle driver, this will remind you of how pistons generates revolute motion. Then this is changed in direction into a transmission cam. And then you have a pinion and a gears that will let rotate the rear wheel of your motorcycle. It's exactly through transmission devices. You have the motor on one side, in that case, not an electrical motor, but a mechanical energy transforming motor. So this qualitative transformation is another basic important. And finally, the presence of transmission, which relocates the load from the actuating motor. We have already seen this in some example of robots, where these motors can be placed close to the base of the structure, so needs not to be carried around by the robot itself. Through this connection and transmission and reduction element, we can remotely drive links with motors that are placed on the base. And we gain much efficiency because with the same motors and powers of these motors, we can accelerate and move links of higher mass, of larger mass, thanks to the presence of these transmissions. Okay? So this is another very important aspect. So let's see a few elementary transmission here. I've downloaded this from the web. There are, again, a huge number. I like this for the colors. Essentially, I've chosen this. So on top, you will see the so-called rax and pinion structure. And in this video, the first one, you see one possible relative motion where you have some revolute motion which is transferred into a linear motion of the upper rack. In this case, the lower rack is held fixed. Okay? So you're rotating the wheel with their teeth engaged in the upper and lower rack. The lower rack is fixed and the upper rack is moved. This is not very convenient for a robot application. Why? Because you have seen that there is a translation of the axis, of the revolute axis of the wheel. But if you imagine that the wheel axis is held fixed by some support, and you're rotating this, then the two racks will move linearly, like this. Okay? So you're converting a revolute motion into a linear motion, exactly what we would like to have. And also, you can have a scaling factor depending on the radius of this wheel, so on the number of teeth that you have on the external circle. You may have that one rotation of the wheel is equivalent to some displacement. And by changing these numbers, you change the ratio between angular motion and linear motion. And you obtain already a kind of reduction. But here you are changing the nature of things. Okay. Here there's another situation which is, okay, let's see. This is a epicycloidal gear train. So you have two wheels, teethed, engaged, with a different number of, with a different ratio, and thus with a different number of teeth. The number of teeth is very important, but it's related, strictly related to the radius of these wheels. And now this small gear is rotating outside the large gear. This is called epicycloidal gear train. There's also a hypocycloidal where the small wheel is rotating inside the large wheel. Of course, the teeth are looking inside in that case. So I've chosen just one of these. And now you can see that the speed of rotation of this wheel is much lower than the speed of rotation of this external wheel, just because of the difference of radius or of number of teeth. Okay? And so this realizes, if you take one input axis and the other output axis, it realizes a scaling of angular velocity. And since the angular velocity is being reduced, this means that the torque on the output axis will be amplified by the same factor. Okay? You can have also this more complex. There are people doing only this, designing novel transmission and reduction elements which have nature of compactness, of being, let's say, symmetric. For instance, this is not symmetric because while this is moving, this mass is going around. Okay? So it's not balanced as a structure. This is realized by this so-called planetary gear set, which has different way of operating, depending on, here you have a sun gear, which is this inside. Then you have these three gears, which are connected through a planet carrier. So these three gears live on a same solid object. And then you have this external annulus or ring gear. Now, depending on which part you block, you have different behavior. And if you do the computation, you can, for all these elements, you can come out with a number, which is the reduction ratio of the elementary gear, which tells you, if you're taking one input as the driving motion and one output as the resulting motion, what is the reduction or the factor n larger than 1 of the initial velocity to the final velocity. So large initial input velocity, low output
final velocity, and vice versa for the produced torque. So here, for instance, you see in the same video, 3 changing situations. Here, you see that the ring is moving, but these are fixed. Now the planet carrier is moving, and the sun gear is fixed. And finally, you fix the ring gear, and while rotating this, you see that everything is rotating with different speed. And counting the number of internal, external teeth, so the relative radius of these devices, you can come out with a number, which is the reduction ratio. By the way, this is very convenient as arrangement, because you see, when things move, the center of mass is always here. Because this triangular structure keeps the balance. So this is a very convenient design. So just to have a feeling of why people get involved in such complex mechanisms. So here again, other types of more complex situation. For instance, you call spur gears, all this elementary type, but where these were all planar. So all axes were parallel of the things that were rotating, except for the rack and pinion. So for rotating parts, everything was planar, was parallel. Now, of course, if you have to change this, you have 2 engaged teethed rings at 90 degrees, or even not at 90 degrees. When you're rotating one, the other is rotating, maybe at the same speed, but you have changed direction of the axis of rotation. This is also very important. All these are called spur gears. Or to transform linear motion in angular motion, or vice versa, you have these lead screws, or worm gearing in Italian, for those that may not be familiar. They are also called vite senza fine. So you have a screw that can rotate and never ends, and this rotation is transferred into a linear motion of some body connected to this gear. And then you have other things. For instance, in the SCARA type, and now I can make another picture. On SCARA type robots, you have a transmission. I mean, some of the transmission is made by toothed belts or chains. Even in motorcycle, going back to motorcycle, you have chains, but now you have some big motorcycles that have toothed rubber belts for transmitting power to the wheel. So in the SCARA type, we have this situation. We have first joint axis, then we have second joint axis, still vertical, so this is the base. Then we would have a prismatic joint that goes up and down, and at the end, a final revolute axis. And then this is the schematic, okay? It's clear to everybody. So this is the pure kinematism. All axes are parallel. These 2 axes are even coincident, because you have the prismatic axis coincident with the revolute axis. Now, where are the motors placed to actuate these joints? Well, typically, one motor is placed here. So this is motor 1, and this will let this rotation by an angle θ1 occur. And the second motor is placed again here, motor 2, and then you have a belt going around. So with this motor, you're actually letting the elbow move, okay? So you're using, in that case, almost all the SCARA type are done like this, a toothed belt. Toothed because it has teeth, it has gears at the end so that it doesn't slip. But of course, it's a rubber object, so it can deform a little bit, so it introduces elasticity in the transmission, okay? If you're giving too much torque with the motor, the transmission will tend to deform and then to transmit the torque to the remote link. Okay, so this motor is moving this link through this joint. This motor is moving this link, so the forearm, through a transmission belt and then moving this joint. Okay? What is the advantage of this solution with respect to the other solution, which would be simply to have a second motor here, M2 prime, directly along the axis of the second joint? What is why this solution is better than this? Because those motors, they spin, their rotors spin, but their center of mass is always fixed. So you don't have to carry them around while the robot is doing like this. Okay? So this mass does not count at all. If you put the motor here and you're trying to move the structure, you have to move the link weight plus the motor weight. Okay? So you need a larger motor to move the same, to give the same acceleration to the actual structure. Okay? So this is the simplest example that I can imagine of an advantage of relocating motors and using transmission elements like this. Actually, just to continue in this example, there are another set of transmission and reduction elements which are called harmonic drives, and we will see them next time, probably, no? Are we done with the class? I don't remember, 5:30 or 5:15? 5:15, so we are done. So let's conclude with this, just to mentioning that harmonic drives are, again, reduction element and transmission element like before. But they are very compact. They achieve very large reduction ratio of the order of 200 rounds of the motor, one single round of the driven load, without backlash. So without the fact that the teeth may have some relative motion, which is a place where you lose power, so you dissipate power. Okay? So they are very compact. They remain in axis, so this is why they are called inline. So there's no different axis. And the harmonic drive is used for this motor. So this motor drives the first joints not directly, but through a reduction element, transmission element, which is an harmonic drive. Okay? So you don't need to displace axis here. So this is why it's conveniently to use harmonic drives in line. You may use small motors, but then produce large torque because these harmonic drives have large reduction ratio. So 200 rotation of the motor is 1 rotation of this, which means that if you have a motor with 1 Newton meter as output torque, after the reduction you will have 200 Newton meter available, a huge amount of torque. Okay? But because of their construction, they introduce elasticity, just like this. Just like a belt of rubber may be compressed or deformed if subject to large variation of torques at one end, the harmonic drive in its own operation tends to introduce some rotary elasticity. And I stop here, but this elasticity is intentional in this case. This is why the name of selective compliant arm. Because these arms are compliant on the plane of motion because of this transmission, while are very stiff in any other direction. And this compliance is useful for doing insertion operation. These SCARA-type robots are mostly used for assembly, where I have to take an object and insert it into a hole. For instance, an IC component on a motherboard with their pins that has to enter in the holes, and small errors in the position laterally
are accommodated passively by this compliance of the structure. So in this direction, in the plane, the system is automatically compliant and adjusts to small positioning error. While going up and down, everything is very stiff and I'm very accurate. So this is intentionally introduced through the use of proper transmission element. And we stop here and see on Friday.